A simplified plot of simplified heat treatment cycle you can see. The first one is, you remember? This is what exactly? This is room temperature. So this is room temperature. This temperature is the predetermined temperature, right? And this is your holding time, heating time. This much is holding, and finally this much is cooling time. Just I have drawn projections to find out the time, because x-axis is your what? Time, y-axis is the temperature. Right? Very simple diagram, no need to remember anything. So this is heating cycle, this is holding or soaking cycle, and finally this is cooling cycle. Okay? And you can understand what is heating rate. Heating rate means from here to here. Suppose this is room temperature, take it to 25 degrees centigrade. So suppose this is 1000 degree. So that means from 25 to 1000 degree I am keeping here, and time here with respect to time. So I am keeping here means suppose time is 0. You are holding it for 2 hours maybe, or it is taking 2 hours to reach this predetermined temperature. So by 2 hours. From room temperature to 1000 degrees centigrade, how much time it is taking? So it is 2 hours. So if you divide them, you will get the heating rate. But do you think that the heating rate will remain same up to 1000 degrees centigrade? It will not remain same actually. What exactly happened in the real situation? Initially, whatever heating rate you have given as an instruction, because they are equipments, right? We do heat treatment inside a furnace. You have seen, everybody has seen the furnace. We have in physical metallurgy also and in the ground floor, right? Yeah. So basically we give instruction that I want to heat my sample from room temperature at this heating rate, about 10 degrees per minute. Mostly people do research at this particular heating rate, 10 degree per minute. That means every minute there will be 10 degree rise in temperature. Suppose initial sample is at 25 degrees centigrade, room temperature, it will reach to 35 after 1 minute. Again after 1 minute it will become again 10 degree rise. So yeah, 45. This way the temperature will rise. But basically the temperature will rise in this way up to maybe around 400 degree or maximum 500 degrees centigrade. In this way. But after 500 degrees centigrade, automatically the temperature rise will be slowed down. Even if you have given instruction, but it will not happen. So that means at higher temperature, heating rate will automatically get affected, it will slow down. It will not rise 10 degree per minute. It will be maybe 5 degree or maybe 8 degree, maybe 7, depends. Basically. It happens actually in real situation. Okay. But it doesn't mean you will not give a heating rate. You have to give heating rate, but it will go on like this. Is it okay fine? So you have to remember. So heating rate will not remain constant throughout the temperature. At too low temperature it will remain same, but at high temperature it will reduce automatically. Okay. Is it fine? And what is predetermined temperature? Predetermined temperature means, see, heat treatment is a subject, but it is having different kinds of heat treatment again. Different types. Like if you have heard about maybe normalizing, annealing. Annealing term you might have heard. Because you have visited industry, you know that people do annealing after cold working basically. If you have visited cold rolling mill, you have seen that once they do cold rolling, and if they want to reduce the thickness more and more, they cannot do again cold rolling directly. They need to do annealing in between them. They do cold working, they will reduce the thickness, but the metal will become so strong, so hard, you cannot roll it further. Otherwise there will be breakdown in the roller. So they do heat treatment to make it stop or to increase the ductility, you can say. You understand my point? Then again they do cold rolling. So this is the way. Suppose further they want to roll it again by cold rolling, then they need to do annealing again. Some people go intercritical annealing also, these are terms. Anyway, you understood my point, no? So predetermined temperature actually depend upon what kind of heat treatment you are going to do. Whether you are going to do normalizing, there is a one kind of heat treatment now. We'll study in details. Normalizing, one is called annealing, one is called hardening. Some here. Not here. Okay. So different heat treatments needs different predetermined temperature. It is already there. Suppose you have a particular kind of steel. Already there will be a book. From there you can read and you can do the heating at to that temperature, basically. But listen carefully, this is very important now, what I am going to say right now. Basically, in case of steel, predetermined temperature is the temperature where complete austenite will form. Basically, not always. Not always. That means we need to take our steel where complete transformation will take place to austenite phase. You understood? Suppose for example low carbon steel. Low carbon steel at the room temperature, what kind of phase will be there? Okay, let's do from lecture and on. From iron carbon phase diagram, if you have low carbon steel will maybe less, suppose hypoimpactoid steel. You remember this thing? Hypoimpactoid and hyperimpactoid. A hypoimpactoid steel you have. Hypoimpactoid steel means what? The composition of carbon will be less than 0.77 or 0.8 weight percent. So what kind of phase will be there in that steel? You have the ferrite. Only ferrite. Perlite will be there, of course, these two things. But perlite is a micro constituent, it's not a phase. It's a mixture of phase. People get confused many times. If somebody will ask what is perlite, you have to say it is a micro constituent, or you can say it is a mixture of phase. Because ferrite will be there and cementite will be there. Ferrite will be one phase, cementite will be another phase. So some people also call, if you go through my videos as I talked about, it is a bicrystallization. Two different crystals are there. Ferrite is one crystal and cementite is another crystal. They grow and penetrate into one another in 3 dimensions. Anyway, so my point is initial microstructure is what? You have ferrite cementite mixture and ferrite also. Right? But if you want to do heat treatment, what you do, you take it to about around maybe 912 degree or 920 degree or 950. So that what will happen? All the perlite, all the ferrite will become austenite. There will be a single phase only. That means at the predetermined temperature, you have only austenite phase. No ferrite will be there, no perlite will be there. Everything becomes austenite. So now, this is a question from my side. You don't answer it, I know. From last bench, can you tell me why we are doing this? Why we are taking the steel to austenitizing temperature first? Then we are doing holding, then we are doing cooling, right? Can you tell me? Please raise your hand at least. Why we are doing like that? We are taking the steel to austenitizing temperature first. You people understood or? At room temperature, suppose you are dealing with a hypoimpactoid steel, you have ferrite and perlite, right? You need to check what is the predetermined temperature. Suppose predetermined temperature is 950. So you take the steel to 950, what will happen? All the ferrite, all the perlite will transform automatically to the austenite, right? Phase, that is called phase transformation. Already you have studied now. Perlitic phase transformation you have studied already, right? So why we are doing that? Why not below austenitizing temperature we are doing? Or why we are not taking it to so high temperature, just below melting point maybe? You are saying something. Can you justify it? I mean, change in crystal structure means what? New grains will be formed. Okay, fine. Those are actually austenite grains. Grain coarsening will occur. No, we don't want grain coarsening. No. Okay, let me give you a hint. Why we are doing heat treatment? We are doing heat treatment so that we can modify the structure. It may be crystal or it may be microstructure or crystal structure. Why? If they will change, then property will change, then performance will be better. So can you tell me now, right now? I told you the hint already. The last cycle is cooling cycle. Yes, from austenite you can transform it to some other phase. That's why we are doing cooling. If you do very fast cooling, you will end up with Martin cycle. Very hard and brittle, basically. If you do slow cooling, maybe again perlite will form. But that perlite may be finer. It depends upon cooling rate. If you compare the size of initial perlite and after cooling, there is a size of another and the size of perlite. So size of grain is changing. So what will happen? Of course, your property will change. Your grain size also may change. The entire grain. If initial grain was bigger, you do very fast cooling, you will end up with perlite, but your grain size is small now. So you have improved the toughness or strength, right? Shall I tell you again, or is it okay? So we are always, basically, not always, mostly we are taking the steel to austenitizing temperature, so that initial phase will become austenite. Then when we cool, we can cool at different rate, slow, fast, medium. So if you change the cooling rate, the product will be different. The phase which new phase will form will be different. And according to your requirement, you can do. If you want very high hardness, you produce martensite, just quench it. Your hardness will be drastically improved. If you want ductility, you do very slow cooling so that the grain will be coarser. Slow cooling means what? You need to keep it in the furnace for more interval of time at high temperature. So grain growth will be there. Right? So final structure will be a coarser grain. So ductility will improve. Is it fine? Is it okay, or? So that is you might get a question from this. Like, why basically we take the steel to the austenitizing temperature during heat treatment. You can write it now. Because we need to do phase transformation according to our requirement. And particular phase will decide the properties. You can write. So if you want benite, you people remember benite phase? So why we sometimes need benite phase? What is the advantage of having benitic phase? Like martensite is very hard and brittle. So if something is very hard and brittle, which property will improve? Hardness obviously, but it is linked with which kind of property? Wear resistance. Material will not remove from the surface. If there is friction, material will not remove. Higher is the hardness value, higher is the wear resistance. You have to remember. It is very important property. Like railway tracks. Train is always moving. There is friction always. If it is not harder, so the thickness of the track will reduce with time, no? Then it may collapse. Of course, it cannot withstand very high load after some time. The thickness will reduce, right? Anyways, you understood my point. If you want to increase the wear resistance property, then you have to increase the hardness. So you can produce martensite simply. But what is the advantage of having benitic structure? Toughness, very good. If you want very good toughness, you can produce benitic structure. That is a very interesting point. And to improve toughness, what can be done also? You can reduce the grain size also. That is also very interesting. If you don't want to produce benite, you have an option that you can reduce the grain size. You can produce that also. So grain size refinement, that is called grain size refinement, means you can produce smaller grains. So small grains and benitic structure will give you very good toughness. Suppose you want to produce a bulletproof jacket, for example, using steel. Let it be. By using steel, you want to produce a bulletproof jacket. You can produce benitic phase in that. It will stop a bullet to go inside. Anyways, you know that China, most of the railway tracks of China is made of this benitic steel. The railway tracks. But in our India, do you know which kind of steel it is? Perlite. Steel it is perlite. So what is the advantage? So that's why they are running bullet trains and all. Really? That's why their train speed is very high. It's not like Vande Bharat. 2 hours, 3 hours late. Anyways, you are paying more, but nothing is working. Anyways, so up to this it is fine. You can draw a simple diagram of heat treatment cycle, heating, cooling, heating rate, cooling rate and all. Okay, heat treatment variables, it's simple. Heat treatment variable is heating rate, predetermined temperature, holding time, cooling rate. If you want, you can write. This diagram itself is showing variables. Why they are variables? Because if they will vary, the property will also vary. That is the thing. First is heating rate, second one is the predetermined temperature, third one is the soaking time, last one is the cooling rate. These are the variables. If they will change, then your property also get changed, because you may end up with different phases also, or your microstructure may change. It is okay. Fine. Furnace I told you already. Furnace is a it is a kind of instrument, you can say, or yeah, basically it is an instrument that can take the temperature to very high. Fine. So what are there inside the furnace? That means inside the furnace what is there? How we can go to very high temperature in the furnace? Huh? Refractories, okay, refractories. But refractory alone cannot take. Refractories are there to protect the steel, because outside of the furnace is made up of steel, but inside is refractory. Refractory means ceramic material. Outside is steel, metallic material, right? Metallic material cannot withstand such high temperature. No? It may get oxidized or it may damage with time. But ceramic material can withstand very high temperature. That is the main advantage of ceramic. No? It will not melt or it will not fuse. That is called refractoriness. The property is called refractoriness. Anyways, they are heating coils actually. Like heater, you have seen the heaters? Anybody have seen heaters? Who used to cook? So they are coils, right? They are nichrome wires, basically, nichrome wires. No? But, not tungsten, tungsten is that is actually, they use in the bulb earlier. But we are using LEDs nowadays, no tungsten coils. Anyways, my point is, inside the furnace there are coils or there are rods. Some furnace, if you see, sometimes you can ask Ratnakar to show you the rods. There are heating element, that is called heating element. Heating element means that can withstand very high temperature, but that has very high resistivity. You are flowing current, resistance is very high. So what will happen? I square R loss will be more, so lot of heat will generate. By I square R loss, you know that is I square current and resistance. Okay, those are called heating elements, and basically they are made up of canthal. You can write if you want, and you can check the composition. Canthal, super canthal. K-A-N-T-H-A-L, canthal, and super canthal. K-A-N-T-H-A-L, canthal, super canthal. You can check the composition right now. Can you tell me? Some rods are made up of silicon carbide also. Maybe you can check silicon carbide. I think canthal and super canthal molybdenum disilicide. I think just check molybdenum disilicide. Not sure. I forget it. No. This canthal is iron chromium. Yeah, okay, fine. Super canthal. Can you check? Molybdenum, oh, yeah. Can you check how much temperature you can go in super canthal and how much temperature you can go in canthal? That is the limit. Okay. 1800. Yeah. So that means if you want to go for very high temperature, you can use super canthal as a heating element. That will provide you heat energy. But if you want to go to 1400 like that, then canthal is fine. You cannot use canthal for high temperature, otherwise it will melt or it will destroy. Get oxidized. It is fine after this. Okay. Then, okay. So listen carefully. Sometimes the furnace atmosphere is also important. The atmosphere inside the furnace during heat treatment is also important. How many of you have visited to Hindalco during your training? FRP. In FRP they have annealing furnaces, right? New annealing furnaces. So in that new annealing furnace, what they are purging during annealing? Hydrogen, are you sure? Nitrogen, yeah. Argon or nitrogen? Nitrogen. So can you tell me why they are purging nitrogen in the annealing furnace? Blast. No, nitrogen is an inert gas actually. Inert gas means it will not react with the steel surface. That means oxidation will not occur. If you normally heat the steel in normal atmosphere, like you take a piece of steel and put it in our normal furnace and heat it to 1000 degrees, it will oxidize. A scale will form, a oxide scale will form, and it will remove also with time. You keep it for more interval of time, right? But you don't want to destroy your samples, right? To prevent oxidation or to prevent corrosion, actually oxidation, right? To prevent oxidation, we need to maintain an atmosphere. Basically, what kind of atmosphere? Reducing or maybe neutral. Either you better we people use neutral atmosphere like nitrogen, argon during heat treatment. Right? Or you can use reducing atmosphere like carbon monoxide and all, you can use it sometimes if it is required. Is it fine? You can write also, this is one kind of variable also you can say. Atmosphere of the furnace. Whether it's neutral means nitrogen and argon, reducing means reducing gases will be there like hydrogen or carbon monoxide. Oxidizing atmosphere means normal atmosphere oxygen will be there. Okay, but we don't use most. This is very interesting. Condition of different heating rate. So when we need high heating rate, when we need low heating rate. Let me draw this diagram. This is for example your carbon steel. This is stainless steel. This is same metal. Second one, this is also same metal. Okay, fine. Otherwise, there is random diagram can draw. But this versus this. You can understand this one. Now can you tell me, see we are now discussing about the heating rates. That means when we need high heating rate, when we need low heating rate. We cannot do always a particular heating rate. We have to see, we have to check first. Or ingots for example. After casting you are getting ingots. At what rate you want to heat it for example. So it depends. The first one you can see comparison between carbon steel. Suppose this is low carbon steel. Right side is stainless steel. So can you guess in which case we need high heating rate or low heating rate or same heating rate? Carbon steel high heating rate and stainless steel low heating rate. But why? Can you justify it? Any idea? Both are metallic materials. Both have same. Both are metallic materials and they are good conductor also. This because it is metal basically. Yeah, because of alloying elements. Very good. In plain carbon steel you have iron and carbon only, right? Majority is iron and small amount of carbon. But stainless steel, suppose 18:8 stainless steel, 18% chromium and 8% nickel is there. So lot of alloying element you have added already. Apart from carbon, you have added lot of chromium and lot of nickel. So what will happen? It is a solid solution, no? Of course. It is a solid solution. Which kind of solid solution is it? Solid solution is which kind of solid solution? Interstitial. Substitutional, because size are same and nearly. Size of nickel, size of chromium, size of iron are nearly same. They will occupy the main lattice point, not at the interstitial side. On carbon steel is a interstitial alloying element. Alloy, fine. Is it okay? So basically that means in case of stainless steel, heating rate should be slow. But in case of plain carbon steel, heating rate should be high. Why this is? Because the point is in case of stainless steel, because of lot of alloying elements, the thermal conductivity will be affected by that. The thermal conductivity is 4 in case of stainless steel, you can write. The thermal conductivity of stainless steel is 4 compared to normal carbon steel. Because of, you can write because of solution, because of what it is because of heavy alloying. Because of heavy alloying. Technically it is called solution scattering. You can write. The concept is called solution scattering. Solution scattering, can you just imagine what it may be? Scattering means what? Electron want to flow, but it cannot flow in the straight line, it will scatter here and there. So resistivity will increase, very good, the resistivity will increase. Right? See, suppose from here to here, electron want to flow from here to here, right? In this distance, right? If it is a plain carbon steel, electron can easily flow like this, no issue. But if this is a stainless steel, lot of other, apart from iron, other alloying elements are there. So what will happen? Some strain will be there in the body. Why? Because some atom will be bigger, some atom will be smaller. So there will be a lattice strain will be there, right? Localized lattice strain. Because of this localized lattice strain, when electron want to flow in straight line, it cannot flow. It will move here, it will move here, it will move here, here, like this, and finally it will reach. So it will take time. Conductivity depends upon the flow of electron only, no? From one position to another position. Okay. But that means in case of plain carbon steel, electron can easily flow without any scattering. But here scattering will happen because of lot of alloying element, and lot of alloying element give you lot of lattice strains. This strain will prevent the easy movement of electrons. Lattice strain, how you understood? Because some atom will be small, some atom will be big. Obviously, if same kind of atoms are there will be no lattice strain basically. But different atom will be, because somebody will compressing, somebody will be contracting, like that it will happen. You understand my point? Suppose in this room, I will ask lot of like Big Show to come into this room. What will happen? Big Show means I am talking about the wrestler. Big Show, right? Big Show, right? So lot of Big Show will, if they will come in this room, what will happen? You will be compressed, of course. So it's kind of lattice strain because your size and his size will be lot of difference in that. Same thing happened in this case also. And you know that because of lattice strain also the strength increases. That is one of the funda. If you want to increase the strength, then you can produce lattice strain in the body. Automatically strength will increase. Why? Because the lattice strain cannot allow the dislocation to move easily. They are hindrance actually. So that is your martensite. Because of formation of martensite, there will be lot of lattice strain in the body. That increases the strength. That is also the condition why solid solution we are doing. We are doing solid solution strengthening because lot of lattice strain will generate. Carbon atom always go into the industrial sites, right? It also generates lattice strain around it where it goes. So strength will increase automatically because dislocation has a strain field and your lattice also has a strain field. They will interact and dislocation will stop. It cannot easily move. You have studied now interaction, dislocation, interaction, dislocation interact with atoms or molecules or these things. Already you studied in maybe DBM, I guess. Yeah. Okay, anyway, you understood my point. So in this case, you need high heating rate. In this case, low heating rate. But why? Suppose I want to do high heating rate in case of stainless steel. What is the problem now? Just think of it. What may be the issue? You can give high heating rate. Your choice, right? You say I want to do very quick heat treatment. I will give a high heating rate, 20 degree, 30 degree per minute. So what is the problem? Melting point. No. What will happen to the stainless steel if the heating rate will be high? This thing I am talking about the condition. If your boss will give you a stainless steel, you join a company and you want to do some heat treatment, you should not heat it at a very high rate. Otherwise there will be, instead of gaining good property, you will lose that. What may be the reason? Can you tell me? Already I told you resistivity is there. So, and the hint I can give, the surface will be heated up first. Then, lot of difference of temperature will be there. Because the surface will get heat up to 1000 degree for example, but inside still the temperature is very low. So there will be thermal shock. Cracks may generate inside the material due to thermal shock. You want to finish the experiment very fast, or you want to do your job at a very fast, but it is not recommended because thermal shock will be there. You understand my point? Because this part will heat up very fast, but inside the temperature will be less. Because it needs more time to travel. That's why. But if you heat this one, all the part will be at same temperature after few minutes or something. Is it okay? So that is the reason actually. Now can you tell me in this case and this case? Both are steel. But one is having cross-sectional area is more, cross-sectional area is less. Or thickness is more, thickness is less. In this case we need more heating rate and slow heating rate. Okay? Right side? Just we have discussed it now, no? Just right side will need slow heating rate because the cross sectional area is more. So heat cannot travel quickly to the center. So there will be thermal shock again. Is it okay? So in this case, the thickness is more. That means to travel the heat from this location to this center take more time, of course. So there will be a temperature gradient, there will be a thermal shock. Thermal shock means it may generate some cracks. Do you know that if you take out a piece of ceramic material from the furnace at 1000 degrees and you put it here, what will happen, you know? It will break into pieces automatically because of thermal shock. 1000 degree to room temperature. Sudden cooling. Why this happens? Huh? Sorry? Uneven temperature, but why? But technically why it is happening? When we take something to high temperature, it expands always. All the solid expands when you take it to high temperature. But now you bring it to room temperature, it will contract. But temperature is still high. It wants to expand, but you are forcefully given to contract. So opposite phenomenon will happen, it will crack. Simple things. Is it okay? At low temperature, contraction happens. At high temperature, expansion happens. No? Solid expands. Is it okay? That's your thermal shock. Now this one and this one. This is uniform shape, but this shape is not uniform. Somewhere it is less thicker, somewhere more thicker. So, of course, the right side needs slow cooling. Left side needs, because for this portion heating will be fine, but for this portion it will take time. So of course, so that means if you provide high heating rate, then in between this part and this part there will be temperature gradient and it may crack. So these are the very simple concepts you have to remember. Different types. So that means I can simply say the heating rate depends upon composition, heating rate depends upon the dimension also and shape. And last one, you can see sharp corners are there, and in this no sharp corner is there. Material is same, no? Steel maybe. So what do you understand? So in this case it is low, in this case it is high because sharp corners are there. You know that sharp corners are always stress concentration sites. You know this from DBA. That's why you always prevent to have sharp corners in structural application. Whenever you are using something in structure where it can withstand very high load, you should not have sharp corners. What will happen? If you have sharp corners, the distribution of load will be not same. It will be more at the sharp corners. So there cracks will form and finally it will fail. But if the structure is uniform, no sharp corners, the distribution of stress will be same everywhere, no problem. You have to remember, these are very important points. You know that there should not be any groups also. Groups means, okay fine. For example, this kind of structure, it should not be there. Groups. Or suppose this is structure and this is a group, hole in that. So what is the problem? Where there will be a groove, hole, around that groove the concentration of stress will be more and the cracks will start from there only. But you don't know, now you are applying same load on the material. It should be uniform everywhere, but it should not be uniform. Automatically the concentration of stress will be higher along the grooves. Where the concentration of stress will be more, crack will form there only. And that is the limit, that is the main disadvantage. Recently I solved one problem. My sister's husband is in Australia. He asked me that we are facing this kind of problem. He is a mechanical engineer, he don't know this. So I told him that we check it first, this thing. Then they checked it and they got to know that because of these groups and all, their component is getting failed very quickly. It cannot remain for long interval of time. Okay, anyways. So we are the people who solve this kind of issue. We metallurgy people, no? I'm not talking myself. You can also solve. Anyway, so okay, I will end this topic here now.